Hello everyone, my name is Imane. I'm a PhD candidate from Mohammed VI Polytechnic University in Morocco, and I'm glad to be here at NETIS 2021 presenting our paper entitled LightX, a lightweight proof of bandwidth transaction transfer system. This is a joint work with Yahya Ben Kaouz and Ahmed Khomsi. In this presentation, we will cover the objectives and motivation for our work. We will give an overview on existing consensus families, we'll state our contribution and detail its building blocks, and show some experimental results and conclude with a conclusion and some perspectives. Since it was first introduced by the so-called Satoshi Nakamoto in 2008, and up to now, Bitcoin has revolutionized the concept of data trustworthiness and managed to stand the test of time as the world's best known and widely adapted cryptocurrency, in spite of the emergence of a multitude of solutions serving to the same end. Soon after, blockchain, the underlying technology of Bitcoin, represented a key component in various applications such as e-voting, IoT, healthcare, and various management systems, even though it has many inefficiencies. Consensus algorithm, which is the fundamental keystone to achieve consistency and reliability within blockchain, incorporate by its very nature several technical hurdles. We mention the excessive energy consumption induced by the mining activity that leads to huge amounts of electricity being wasted and therefore damages the environment. Low scalability. In such networks, it becomes challenging to operate smoothly as demand increases. Lack of fairness. Popular blockchain systems lack fairness among users, as the decisions are made by users with high computational power, such as in Bitcoin, or holding more stakes, such as in Ethereum. Also, the mining activity in Bitcoin has become highly centralized, with miners forming large mining pools to fasten block production. On the other hand, existing blockchain systems can provide at most 2 out of 3 features of the so-called blockchain trilemma: scalability, decentralization, and security. So, with our solution, we seek to find a middle ground between reliability and scalability guarantees to fit with application demands, while maintaining decentralization in open environments. So, before we introduce our system, let's have a quick overview on existing consensus families. The consensus problem has been a ubiquitous research concept in distributed systems, yet it gained further attention with the enforcement of blockchain technology. However, it still represents at the same time the bottleneck of the system. So, to cope with these issues, emerging solutions fall mainly into one of these consensus families. The first approach is the proof of work, or Nakamoto's consensus and its variants. These protocols are generally robust and they support public environments, but they are energy exhaustive and they induce high latency and a poor scalability. While the second approach focuses on the classical Byzantine agreement and fault-tolerant protocols by introducing probabilistic and asynchrony assumptions to bypass the impossibility results. This approach manages to achieve a reduction in energy and fast performance, but it still scales poorly and have quadratic communication complexity, and also it is not suitable for public environments. So, to conceive LightX, we consider a public peer-to-peer system with authenticated reliable point-to-point communication links, and we assume that all nodes have a direct access to a sampling service to pick their communication samples, and that participating nodes are recommended to dedicate their bandwidth resources for the application, and especially during assessment phases. Nodes newly joining the network are not assigned any reputation score. they get their scores after the interaction with other nodes. And we assume a set of highly ranked nodes that we call pre-trusted nodes. So the first built-in block in Lytix is Byzantine Reliable Broadcast Abstraction, which is deployed here to replace the expensive consensus protocol. The aim of this primitive is, given a sender broadcasting a message into the network, the message is guaranteed to be delivered correctly, even if certain nodes are Byzantine, including the sender itself. Byzantine Reliable Broadcast selects randomly communication samples, which are in logarithmic size, and exchanges feedbacks to guarantee consistent message delivery. The broadcast primitive consists of 3 nested subprotocols or sublayers that operate in the following order. First, murmur, which simply disseminates a message broadcast by a sender. Second, sieve, which echoes the gossip message to check for its consistency among correct nodes and ensure that everybody has heard the same message. Then contagion, which makes sure that all correct nodes take the same decision by exchanging feedback messages to check for the readiness to deliver the message. Byzantine Reliable Broadcast offers many interesting properties. It solves agreement and avoids double spending problem. It is scalable, fast, sustainable, it has reduced communication cost, and it is robust to Byzantine actors. On the other hand, since it is an abstraction, it has poor handling to concurrent events, and it is prone to Sybil attacks, which refers to nodes creating multiple fake identities to take over the network. So, to adopt the broadcast primitive to our system, we enable concurrent transfers by providing the system with routing mechanisms and broadcast identification channels. Nodes need to identify the received broadcast messages according to their corresponding transactions. For this purpose, we create a routing entity at the level of each node, and the router contains a routing table with all the ongoing transactions. Whenever a node receives a broadcast message, it would check in the routing table to map it to its corresponding broadcast channel. And this way, each broadcast channel will carry only a single transaction. The second building block in Lytix is the proof of bandwidth reputation system. In the proof of bandwidth scheme, unlike Nakamoto's proof of work, nodes are required to prove their identities without being exhausted by investing a huge amount of energy in CPU power. Simply put, each node assesses periodically the available bandwidth of nodes with whom it communicates by use of probe messages. A node running multiple identities can be detected by presenting bandwidth fluctuations. The intuition is that the transmitted transactions should be proportional to the used bandwidth resources. So a real identity should reflect a stable bandwidth, while a peer running multiple fake identities will have fluctuating bandwidth measurements caused by the high load. Then we assign local scores accordingly by comparing over multiple rounds the variance of the bandwidth records of each node to a fluctuation tolerance factor and update the local scores as follows. We normalize the scores, and then these scores are aggregated into global scores via setting up a reputation system. Global scores are computed by iteratively querying remote nodes for their evaluation of other peers and weighting their remote evaluation with their local scores. This process is repeated for a certain number of rounds. When the updated scores stop changing over iterations, we say that we converge to a global score. Our empirical evaluations demonstrate appealing results. First, contrary to the quorum-based version, the communication cost to reach agreement in sample-based Lytix is logarithmic. Second, The latency of LiteX is reasonable, reaching 12 seconds in a network of 250 nodes. Third, LiteX reaches a throughput of over 500 transactions per second, and this transaction rate decreases with the number of nodes, but it remains clearly higher compared to Bitcoin, which can only achieve 7 transactions per second on average, or Ethereum that reaches 20 transactions per second. Also, we have here the convergence speed of the reputation system with different residual values and with different network sizes. And on the right, we have the bandwidth estimation that shows the difference between honest nodes and Sybil nodes bandwidth capacity to validate one transaction as the number of fake identities increases in the network. So in brief, we have presented the practical and scalable transaction transfer system in public networks that bypasses the limitations of blockchain consensus. LiteX leverages Byzantine reliable broadcast primitive to transmit and validate transactions, and a proof of bandwidth-based reputation system to deal with the threats enforced by Sybil attacks. In future works, we intend to formally analyze the practical usage of LiteX and provide it with additional features to enable its adoption as a cryptocurrency system. That's the end of my presentation. Thank you very much for your attention.